some first speaker, this known as Zhou, who is a great student at Hawaii University, really great next year. And today he'll tell us about causal duality and categorifying Jacobi.
Thanks for the introduction. I'd like to thank the organizers for allowing me to speak here. Right, so today I'm going to tell you a little bit about Koszul duality and categorifying Jacobi Trudi. So I lied a little bit on my abstract. It's going to be flipped around. I'm going to talk about Koszul duality first. And then if we have time, we'll talk about Jacobi Trudi later. Right. So if you'd like to follow along, you can find the link to the Beamer slides on my website. There's a talks page, and if you just copy paste this URL, you will be able to find the slides. Right, so let me begin by talking about Koszul duality. So I'm going to begin with the slogan. The slogan is that if you have some algebra A that you care about, the representation theory, the Koszulity of half of A, whatever that means, is intimately connected to BGG resolutions. And it seems like a lot of algebras appearing in nature, quote unquote, or appearing in categorification have this property that half of it is Koszul. So this is what we're calling nil Koszul. And the other half of the slogan is that in good cases, Koszul duality with respect to this half algebra is the BGG resolution. So that's kind of the main takeaway from this talk. So that's the most important part of the talk first. Sorry? Oh, yes, let me, sorry, I don't have a slide for this. So maybe let me write on the board to briefly recall what the BGG resolution is in the classical context. So in the classical context, in category O, you can imagine maybe for SLN, you have a simple module labeled by the identity element of the Weil group, and there's a resolution of this by Verma modules, which I'll call capital delta. So let me write that. Maybe this is the Verma module, and then the rest of these terms are going to look like direct sums over Verma modules labeled by Weil group elements, where the Weil group element has fixed length. So it's kind of like the kth term of this resolution has direct sum of Verma modules of length k, and then eventually it terminates because the Weil group is finite. So classically, this is what happens for category O. This is what's known as the BGG resolution. BGG here stands for Beilinson, sorry, Bernstein, Gelfand, not Beilinson, Bernstein, right? So that's classically what happens. And suppose there's some other algebra A generally that you care about. So this could be temporally Lieb, this could be Brouwer, this could be Sergel, this could be a lot of different things. And you care about the representation theory of that algebra, you want to come up with an analog of a BGG resolution. So this is what that is talking about. If I want to find an analog of BGG resolutions, this is the sort of thing I should want to study, whether you can find half of it that's Koszul. Yeah, so for example, we're going to talk about Sergel today, and this is also the case for temporally Lieb, and I'm sure it's true for many others, which I will study in due time, I guess. So for today's example, here's what to think of. If you're a representation theorist, you might prefer to think about the central block of category O for SLN. And really for today, you can just pretend n equals 2 or 3. If you're a geometer, what you might prefer to think about is constructible sheaves on the flag variety with respect to the Bruhat stratification. Again, you can just focus for n equals 2 or 3 really for today's talk. And if you do diagrammatic algebra, which is kind of the area that I'm in, this is what we'll focus on today, what we'll think about is modules over some algebra. This algebra is known as Sergel calculus or Sergel modules. And sometimes people put a cyclotomic in front. So what is this? What does this mean? This is, for experts, what this is endomorphism algebra of some direct sum of Bott-Samuelson bimodules or Sergel bimodules. Okay, so let me tell you about what is this Sergel calculus. So Sergel calculus S, I'm calling it S, is some graded algebra. Elements of this algebra are spanned by certain pictures or diagrams. Multiplication in this algebra is just kind of you stack diagrams vertically on top of each other, just kind of putting pictures together. And what do these pictures look like? These pictures locally kind of look like things like this. They have degrees given down here, and as well as these upside down flips of these diagrams. So here, what are the colors? The strings of these pictures are colored by nodes of your Dynkin diagram. For our purposes today, there's only going to be like 2 colors at most, so we won't worry about, for example, this one too much. Yeah, each string is colored by a node of the Dinkin diagram. So in this case, red and black are adjacent nodes on the type A Dinkin diagram. And we will only consider pictures where the top and boundary of the pictures correspond to subwords of some reduced expression for the longest word of the wild group. You can really replace the longest word with some other thing, but this is a technical thing that we'll talk about later if we have time. So all of that's a lot of mumbo jumbo. What's an example? So this is a central example we'll focus on today, or one of the central examples. There's a 5-dimensional algebra. It's mode equivalent to category O for SL2. It looks like this. So here you can see the top and the bottom of this picture are both just S, which is the longest element of the wild group S2. Here it's also S, S. This is S. The top is the identity. The empty string is the identity. Here this is identity to S and identity to identity. So there's 5 diagrams that I put here. Now you might say, conceivably, I could draw a diagram in the middle where I have a lot of other more complicated things maybe involving this picture or maybe involving this picture. What happened to all these other ways that I can draw these diagrams? Well, it's because there's certain rules for simplifying these diagrams, and I'll tell you about those rules on the next slide. So those rules make it so that these are the only possible diagrams you can draw. Yes,
What makes this degree of this top interval is 1 and this trivalent graph -1?
Oh, this is just like by definition. The definition for these degrees is coming from sort of morphisms between Zergel bimodules, which are these kind of bimodules over some polynomial rings. This is kind of by definition. For this talk, you can maybe just take this as definition. Yeah. And let me tell you about the relations. So these are the these are the relations for one color. It's maybe a lot to look at, but the point is, for example, you can't have something earlier in this picture. The reason you can't have a diagram where you start at S, you kind of do some random more stuff in the middle, for example, you can't draw a circle and then go back down, is because that's equal to 0. Yes, question? Oh, the mirror image of this is also true, yes. Sorry, I should say all these relations hold true up to mirroring and rotation. Up to mirroring and rotation. So these are just kind of local relations. And here are some 2-color relations. And the distant colors will just kind of pull apart. And there's also a tetrahedral relation involving 3 adjacent colors that I'm not going to talk about here. Anyways, the 1-color relations are kind of the most important for today. And there's one extra relation, which is the cyclotomic thing, which is saying that barbells at the far left, we're going to set to 0. Anytime there's a barbell at the far left, I declare that diagram to be 0. So here's a bigger example. Earlier, I gave you a 5-dimensional example that tells you SL2 category O. Here, this 16 plus 4 plus 4 plus 1-dimensional algebra is more equivalent to category O for SL3 modulo simples labeled by these 2 wild group elements. So here, red is S2 and black is S1. Okay, so this is kind of a bigger algebra, but it's still more or less handleable. So the reason I give this example now is because I'll give an example involving this algebra later. Now let's talk about Koszul theory. Just to briefly remind you, a graded algebra is said to be quadratic if it's generated in degree 1 and the relations are all generated in degree 2. So one way of thinking about this is you have, your degree 1 part of your algebra, you consider the tensor algebra over that. That certainly surjects onto your algebra. And this is saying that the kernel of that surjection is generated in degree 2. So I use Q for that kernel for quadratic. And the definition of Koszul is that a quadratic graded algebra is Koszul if the X group from the ground field to itself, and here I assume the degree 0 part is a ground field, from the ground field to itself is non-zero only when the homological degree matches the Koszul degree, the one under which it is quadratic. So this is some type of strong condition on the degrees being kind of concentrated along some diagonal for your algebra, for the X group of this algebra. It's a fact that if A is Koszul, then the X group is isomorphic to what's called the quadratic dual, which is denoted A shriek. Oh, shoot, sorry. This is the quadratic dual or Koszul dual algebra. It's defined very explicitly. You can construct it as you take the dual space of the degree 1 part of your algebra, you take the tensor algebra over that, and you mod out by the orthogonal complement to your quadratic ideal. So here that's kind of the technical definition for what that is. And multiplication on this algebra is just inherited from the tensor algebra. So this is kind of the classic basic setup for Koszul theory. And there's a warning I should make here is that for us, because we're doing these diagram pictures for our algebra, we have to be careful about left versus right. Our algebras are non-commutative. The ground field acts on the top and the bottom differently, so we have to be very careful about left versus right here. So here, when I say this star, I mean the left dual. This one is maybe slightly less well known. This is the Koszul dual co-algebra. So this I'm denoting with the upside down shriek. This is the right dual of the Koszul dual algebra. So I denote the right dual vector space with a check. And what it is the nth piece of this, rather than being the quotient by the orthogonal complement of the quadratic ideal, it's this intersection of this thing. So every consecutive piece has to be in the quadratic ideal. And this is dual to the quadratic dual algebra. And the co-multiplication on this co-algebra is inherited also from the tensor algebra. It's given by this type of a thing. Okay, great. So now let's go back to that 5-dimensional example we were talking about earlier. Let me maybe, sorry. Are the what? Sorry? Are the what primitive? Yes. So what? Yes. So 1 tensor x plus x tensor 1. Sorry, I think I dropped something. Oh, maybe I'll put this on later. Yeah. So for that 5-dimensional example, consider this 3-dimensional subalgebra generated by spanned by these diagrams. So let me maybe just draw the original pictures on the board so you can kind of have them to look at. This was the original 5 dimensions. These are the 5 diagrams that span my algebra. It turns out this is Koszul by letting the degree of this lollipop be 1, just like the circle degree, and the rest of it is degree 0. This is maybe not so surprising because morally speaking, this algebra is kind of C adjoint x mod x squared, because this diagram, when you stack it on top of itself, the boundaries do not match, so it's equal to 0. And the Koszul dual of this algebra is spanned by these 3 diagrams. Because everything is in degree 1 or 0, there's nothing in degree 2, so it's literally the same thing as before, except you'll notice the pictures now have been flipped upside down. And this is the co-algebra spanned by this. And the weird flipping upside down thing is happening because we have to be careful about left duals versus right duals. So for example, because there was no dual in defining the co-algebras are the same right side up as the original diagrams, but the Koszul dual algebra is defined using the left dual, so I have to flip my diagrams upside down. There we considered S plus, so these are kind of my upside down lollipops. I go from a smaller thing to a bigger thing, which is why it's called plus. We could just as easily have considered minus, and the pictures are the exact same. And this is just simply flipping the earlier pictures upside down. This is an anti-involution of my algebra. And here I want to talk briefly about the bigger example because this will kind of demonstrate the BGG differential that's going to come up later. For the bigger example with 4 cells that I talked about earlier, you can consider this subalgebra. It turns out it is also Koszul. The co-multiplication on the Koszul dual co-algebra will send, so for example, this is an element of my Koszul dual co-algebra because this is in the quadratic ideal. This is equal to this in the original algebra, so this minus this is in the quadratic ideal. So this is in Q, so that's in my co-algebra. And the co-multiplication will send this thing to this. You can just kind of read it off. Yeah, that's what the co-multiplication does. And I want you to keep in mind this middle term here for later. The middle term here splits this degree 2 into a degree 1 tensor degree 1, a degree 1 tensor degree 1. And the signs here, this minus sign and this plus sign, will explain the signs in the BGG differential, which we'll talk about later. And these things are kind of somehow just kind of junk that we're not going to care about too much. This is secretly saying some BGG differentials, right? Another way to think of this is kind of via the Koszul dual algebra, but maybe we don't have to talk about this too much. This is just, these 2 relations are morally speaking kind of the sim versus wedge duality, the classical version from BGG. Like if xy equals yx in the original algebra, then xy equals negative yx in the Koszul dual. So now let me define what no causality means, give you a precise definition more or less. So let A be some type of a highest weight algebra. So this is intentionally vague. This algebra could be quasi-hereditary if you're lucky. This could be triangular based in the sense of Rundin. Could be a variety of things. The point is that the representation theory is nice in some way. There's some sort of weight theory. And suppose A has a nil algebra, A minus, such that this is kind of morally speaking my Verma module. My Verma module can be obtained as some left-derived tensor product over the nil algebra. And the key here is that this left-derived tensor product has to be concentrated in degree 0. This is a literal module in degree 0, so I need this to be concentrated in degree 0. If this is true, then you can do some tensor Hom trick like this, which I'll talk more about later. This will be very helpful for computing X groups. And if this A minus is Koszul, then A is said to be no Koszul. So I guess the reason I define this is that it turns out Zergel calculus is no Koszul by letting this lollipop algebra be the nil algebra. So not only is this lollipop algebra Koszul, it has this property about the left derived tensor being concentrated in degree 0, so you can use some tensor Hom trick. And this tensor Hom trick will allow you to compute certain X groups, which I'm going to talk about now, I guess. So because you can use this tensor Hom trick, right, you can just move this left tensor product over to this side as a Hom. So Hom over S from S to identity is just equal to this. And then you get this left over, and now this thing gets moved over here via tensor Hom. And by that earlier slide where the X group is congruent, is isomorphic to the Koszul dual, I know this is equal to the Koszul dual of S minus, and the idempotents kind of get moved to the sandwich, to the left and the right. And it turns out that thing is concentrated in 1 degree. This is the homological degree. This is the Zergel degree. It's a single copy of the ground field, and it's spanned by this diagram. Spanned by this diagram. So this is the analog of Constant's theorem on Lie algebra cohomology. Some type of a strong result on the X groups from a Verma to a simple, to the trivial in particular. So this type of homological information, these X groups, will already allow us to reconstruct the trivial module via Vermas. So this is some sort of a categorical machinery where you can reconstruct the identity functor from a stratification by using some X groups. I'm not going to talk about this too much here today, even though this is a very powerful technique. A concrete shadow of this technique is that you get some sort of functorial spectral sequence built out of Vermas that converges to whatever you want. For example, the trivial module. For today's talk, we will forego this discussion in favor of Koszul duality. So now let me talk about Koszul duality. So this is not the point of view espoused by the original BGS paper. This is more relevant and prevalent maybe in Podzatselsky's work, is that Koszul duality is some equivalence between derived DG modules over some Koszul algebra and co-derived DG co-modules over the Koszul dual co-algebra, which is a huge mouthful. So this is kind of technical, so today I won't tell you about what the co-derived category is. That's not so important. But co-modules over co-algebras is a relatively basic concept, so that's what we'll work with. So this is kind of the equivalence that we'll be looking at. And here the equivalences are given by these tensor products with a tau on top. So this tau decoration is telling you this tensor product is somehow twisted. The differential structure on this tensor product is twisted by some quote-unquote twisting cochain. It's a map from the Koszul dual co-algebra to the original algebra, which is defined just by killing everybody except degree 1. So it's kind of a very violent map. It forgets about everything except degree 1. And this is just some technical stuff. The differential on the two functors is given by this. These are the rules for the differentials, I guess. For our purposes, you can kind of forget about the first two terms here. Just kind of look at the last term. I'll write this down again when we need it. So the point is that you can see in the last term, this tau thing comes up. And remember, the tau kills everything except degree 1. So in this last term, this is going to be focusing on the degree 1 parts. We're going to come back to that in a second. So now let me do the example. So this is the SL2 5-dimensional circle example from earlier. Here's the plus part of the algebra. Remember, it was 3 dimensions, and here I've kind of drawn it in a 2-dimensional plane by telling you this is the Koszul degree and this is the homological degree. So here I'm kind of putting it along this diagonal, and the Koszul dual coalgebra, I'm kind of flipping the degrees, I'm putting it on the other side of this diagonal. So here kind of I'm adhering to the original BGS conventions. For my Koszul duality functors, I'm going to put some reflection and some shearing inside just to kind of make the pictures look nicer. I mean, these things are invertible operations, so it doesn't really matter too much. It's just there for pictorial convenience. The definitions for those things are above. So let me start with begin life with my trivial module. So my trivial module for SL2 is 1-dimensional. It's just a single empty diagram. It's equal to its own reflection. And I'm going to apply my functor, my Koszul duality functor to it. So to apply Koszul duality, first I have to tensor with the Koszul dual coalgebra, which, if you remember from the previous page, was kind of like looking like this. So I tensor that with this. This is what I get. This is what I get. And the next step is I have to shear it. So the shearing is defined by kind of like this. If I'm over here, then I shear it upwards. If I'm here, then I shear it downwards. So the definition is given here. So after I shear it, I kind of move this guy up to here. So that's the Koszul dual of the trivial module. Now I want to apply inverse Koszul duality back to it. So now I reflect it across this thing. I get this. I tensor it with my algebra, and I get something like this. So kind of this part, tensor the algebra, I get this diagonal thing here. And this thing I tensor with the algebra, I should get something here, but turns out this term is going to be 0 because the idempotents don't match. So I get this. And now I have to shear it again. So I have to shear it downwards, and I get something like this. So the last term of the differential previously was given by something like this. So the tau thing only remembers the degree 1 piece. So here, when I apply the co-multiplication to this thing, I need to only remember so sorry, I should have said, this u sub -1, u sub 0 is notation for the co-multiplication. So when I apply the co-multiplication, the tau only picks up the degree 1 piece. So I have to split this x as x tensor 1 and not 1 tensor x. So this only sees x tensor 1. And when I do this rule, this kind of gets passed over to the a side. So this thing gets multiplied over to here. That gives you this diagram. And what you have left is this tensor this. So that's the differential. The differential sends this tensor to this tensor. And let me just redraw this kind of. This is the Verma module corresponding to the identity. This is the Verma module corresponding to the transposition. And the differential is exactly the BGG differential. And so kind of this, what you get is you take your simple module, you apply Koszul duality, apply inverse Koszul duality, and you get back the BGG resolution. So that's the example in SL2. Just to kind of put an example on the board, I'm not doing the full example for SL3 here, but earlier I had told you something about how the co-multiplication for this works. There was a minus sign and there was a plus sign. So in this case, the differential will send that to this and this, and you should compare this to the fact that in this BGG resolution, this map needs to be minus sign, and this map needs to be a plus sign, so that the d squared is equal to 0. Okay, so the signs of the BGG differential are predicted kind of by Koszul duality here. And in higher rank, this is kind of what's going to happen. This is what we were doing earlier, is we did Koszul duality and we did inverse Koszul duality. In higher rank, there's something more complicated you have to do because there are more than just lollipops. But this is some technical mumbo jumbo that we won't talk about here. But there's some modification you have to do. And in particular, if you apply this to the trivial module, then you recover the BGG resolution. Okay, and in the remaining 5 minutes, let me maybe tell you about why I cared about this, which is the Jacobi Trudi part. So this is kind of like a fresh restart, sort of. Okay, so this is kind of like the classical Tale of Two Cities thing. On the one side, we have symmetric functions. On the other side, we have symmetric group representation. This is a very classical story that these two things are equivalent over C. So we can consider two families of symmetric functions. On the one hand, we have the Schur functions, the S lambdas. These are kind of complicated to define, so we won't give a definition here, but the definition is classical. We also have the complete homogeneous functions, where it's hi is defined as the sum of all monomials of degree I. And we have the celebrated Jacobi-Trudi determinant identity, which tells you that the Schur function can be written as some determinant of some matrix of these complete homogeneous functions. In particular, this is an alternating sum, and so it's a very natural question to ask, can this alternating sum be upgraded into a complex? So here's the corresponding classical story on the other side, on the symmetric group side. You have families of modules. On the one hand, you have the spect modules, which tell you all the irreducibles of the symmetric group. This corresponds to the Schur functions. And on the other hand, you have, if you were given some parabolic subgroup, you can consider the induction from that parabolic subgroup up to all of the symmetric group of the trivial module. This is called the permutation module. And this corresponds to the complete homogeneous function. This is dimension, which is given by some multinomial coefficient, of course. And it's also classically known that this decomposes into spect modules, of course, because symmetric group is semi-simple over C. And moreover, the labels on these simple modules kind of look like this. You have one copy of the original label, and every other label is strictly bigger than it in some dominance ordering, in the dominance ordering. And maybe you might compare this to category O, where the Verma module in the growth indeed group has one copy of the simple module with the same label, and every other simple module appearing has bigger label. Okay, so that's kind of like some analogy. You might ask how to make that precise. So over C, as we know, these two things are equivalent via the Frobenius character, which I'll kind of skip the definition of. The point is the Frobenius character goes from the symmetric group representation theory to symmetric functions, and it sends spect modules to Schur functions and these permutation modules to complete homogeneous functions. So the natural question is there some highest weight explanation for all of these phenomena that I just talked about? So more precisely, here's what I want to do. I want to find some ideally quasi-hereditary algebra A with some map from the symmetric group such that the standard modules of this quasi-hereditary algebra restrict to the permutation modules. I want the simple module to restrict to a spect module. And I want there to be a BGG resolution over A, i.e. a resolution by simples of Vermas. Sorry, a resolution of simples by Vermas, such that restriction gives you a resolution of spects by permutations. And this should categorify the Jacobi-Trudi determinant formula when you take the alternating sum of characters. So that's the goal here. And the way we do this is by considering a quotient of cyclotomic KLR. So you start with some lambda that you're interested in, the lambda for which the Jacobi-Trudi you want to categorify. And you get out two pieces of information, some alpha and omega, some weights, and you're going to construct some cyclotomic KLR from this. And you're going to further quotient this out kind of by killing some cells in the cellular structure, and it turns out this quotient is going to be quasi-hereditary, and the weight lattice, the weight poset is going to be some ideal in the symmetric group. The dominant simple will have a BGG resolution by Vermas, and under some map here, so this is some composition of maps here. This is the first thing is just including the crossings of the symmetric group into the Heck algebra. This thing is the Brundtland-Kleshev map. This is projection onto a cyclotomic block. And this is this quotient that we're considering here. So there's some long chain of maps you can construct. And when you restrict along this map, you get this BGG resolution becomes a resolution of spect modules by permutation modules. Right. And you compute homologically by going to circle. So maybe let me kind of skip the literature review. And let me just skip to maybe the final construction. So the final construction is kind of something like, let me just give you an example. Maybe that's better. Let me give you an example for n equals 2. Rather than tell you the construction for KLR, so for n equals 2, we're going to consider kind of a picture like this. And this is the cyclotomic KLR that would come up. I haven't defined the KLR for you, but the point is to just kind of look at this and see that there's 6 dimensions. Compared to the earlier Zergel picture I gave you was 5 dimensions. So if you just forget about this guy, then you kind of get 5 dimensions back. And the reason you have to forget about the guy on top is because he squares to 0. And I should really end soon. So let me just say that, let me just put the main result on the board. The main result is this, is that there's some construction for some algebra, which is no Koszul. It has a finite BGG resolution of the simple module by Verma modules. And when you restrict along some map from Sn to this algebra, you'll recover a resolution of spec modules by permutation modules, and decategorifying will give you will return you the Jacobi-Trudi determinant formula. So maybe let me stop there. Thank you.